topic for this session is towards a unique subsurface imaging by multi-physics joint inversion of geophysical data. The lecturer is Prof. Jide Ogunbu from Seoul University, South Korea. So, Prof. Ogunbo, you have about 1 hour and 35 minutes to deliver your course materials and following by question and answer session. It's okay to you, Prof. Ogunbo? Okay, so the first I will read your CV. And after that, you can share your presentation. So this is the CV from our instructor, Professor Jide Ogunbo, and this is the email address and his education and qualifications: a bachelor degree from Federal University of Technology, Akure, Nigeria, and a master degree from Delft University of Technology, ETH Zurich, and RWTH Aachen, and doctoral from University of Science and Technology of China. And the position now is professor. The previous publication over 17 publications on ResearchGate and over 31 citations. His skills and expertise: optimization of geophysical method, machine learning, artificial intelligence, and applied geophysics. His latest projects and hidden layer artificial neural network architecture, computer code, geophysical application example, and multi-physics inversion of coincident geometrical coordinates from the gravity and its per horizontal data. And the last is accurate and efficient acoustic wave modeling with optimized dispersion objective function on trilinear finite elements. So, Prof. Ogunbo, you can share your presentation now, and the time is yours.
All right, thank you. I think I need to share my screen with you.
Yes, of course.
It's impossible now. Maybe you can allow me to share.
Okay, you can try again, please.
All right.
I got the information. You can stay in this room just about 1 hour. Is it right?
Yes.
Okay, so you can deliver your course, and then we can stop after that.
All right, that's correct. I have about 1 hour because I have another meeting after now. So
okay.
Yeah, but can everybody hear me? Is it loud enough?
Yes.
All
yes,
right.
I can.
That's good. So, but after the presentation, if you still have questions, you have my contact information. You can just send questions to me, and that will be nice. I just got the emergency meeting, I think yesterday, so I need to attend to it as well. So I want to thank Prof. Waudi Apanadi for the invite. Thank you so much. And I hope that we can learn one or two things in this. This is a nice concept and program for the student and the faculty at large. I attended one yesterday about FEM at night, and I really learned a few things there. So we have today, the title of the presentation is Toward Unique Subsurface Imaging by Multi-Physics, Joint Inversion of Geophysical Data. My name is Jide Nusakari Ogumbo. I'm from Nigeria, but I'm currently working at Seoul National University in the Department of Energy Resources and Engineering. I'm going to follow this outline today. Starting from the introduction, we have method, we have some synthetic examples and field example, and then I'll make conclusions. So the introduction, we're talking about non-uniqueness, and non-uniqueness is almost in everything we do, even in very simple mathematical formula. Like you have on the screen, y equals to x raised to power 2. If we say y equals to 4, what is x? X can be 2 or minus 2. And this itself is not unique. The answer that we get is not unique. That is a problem because we need one answer, not A or B. That's the problem. And it's even much problematic when we talk about engineering problems and geophysical problems. If you can have non-unique results in a simple mathematical formula, then you can expect much more in other kinds of scientific and engineering problems. So that's the kind of idea and a way to introduce the subject of non-uniqueness almost everywhere. And to further appreciate the definition of non-uniqueness, we need to examine the concept of model physics through the understanding we closely consider in the full properties of a rock grain in the subsurface. You know, when you look at a rock grain in the subsurface, the rock grain has multiple physical properties. That is, you can talk about the physical properties of a rock grain in the subsurface, like the acoustic impedance. That is the product of velocity and density. You have conductivity, you have permittivity, you have susceptibility, just from a single grain of rock. A rock grain is made up of so many physical properties. Unfortunately, our existing geophysical methods have been developed for just single physics, single parameter imaging per time. So we have something that has many properties, but our method is just looking for one property. Then there's a problem. That's the problem, that's the source of non-uniqueness, because gravity method is going to look for density information of the rock grain. Magnetic will only look for magnetic susceptibility. Low frequency EM will look for the conductivity or resistivity imaging. High frequency GPL for dielectric permittivity imaging, and seismic method for velocity modeling. But this single method inversion is a kind of underdetermined problem where there is not enough data, leading to non-uniqueness. So the consequence of a single physics inversion is the inherent non-uniqueness in the interpretation, because a single parameter, physical parameter, lacks the ability to uniquely identify buried objects. So this non-uniqueness challenge has naturally led to what we can call the multi-physics or the joint inversion philosophy. And that philosophy tells you that two or more parameters or methods should be combined in a multi-objective function in order to take advantage of the complementary attributes that constrain the multiple physical parameters. And this approach will simultaneously solve the underdetermined problem through the provision of more data from more methods. So the point is that when you use gravity to look at the density information, you use magnetic method to say something about the magnetic susceptibility. You have ER, EM, or DC resistivity to talk about the conductivity. By the time you combine the information together, you're approaching a unique definition of the problem. So the purpose of this lecture now is to say that there is non-uniqueness problem that have been efficaciously solved by joint inversion. How do we do that? Why do we do that? What are the roles of complementariness of method and data in the joint and multi-physics inversion? And how do we apply them to solve some of our problems? So the questions that on our mind should be, what are the causes of non-uniqueness in interpretation? How can we minimize the non-uniqueness in interpretation? Will the same kind of data be appropriate for the multi-physics inversion? Do I require a different kind of method and of data? So how do we understand the constraints to impose? We have several constraints in the literature. We have petrophysical constraints. We have cross-gradient constraints, Gramian mathematical relation, fuzzy C-means clustering. How can we improve the confidence of our final inverted models? Velocity, electrical resistivity, and density, and so on. So the concept is that if you are using just electrical resistivity method to get the image, the resistivity model of a subsurface, you don't use any other method or any other data, you're going to be getting just one information from the subsurface. And that may not be reliable because that grain has so many other physical properties that you should examine. So causes of we have the causes of non-uniqueness as described by Jackson D, the 972. It says that if your data is inaccurate, if you have insufficient data, if you have inconsistent data, they are going to give you non-unique solution. And the earliest treatment of this, of the non-uniqueness of joint inversion was started by Vozov and Jube in 1975. And they've been thinking about solving the problem of non-uniqueness a long time ago, as far back as 1975. They performed that. And they recognized the cause of non-uniqueness in geophysical interpretation and attempted to solve them. So we're going to examine some of the published titles in geophysics. Okay. And see how extensive people have applied these methods, because you can, once you see the way people are applying the methods, you can also come up with your own research. Your research topic, you can combine two or more methods together to get a more unique research project. We have Abubakar et al. 2012. They combined electromagnetic data and elastic full waveform data. That's a seismic. You see now they are combining two methods there. And we have Katzer McCausland et al. 2015. They used seismic method and gravity. And we have Gallardo and Meiji 2003. And they use a DC resistivity method and seismic method. And we have Gallardo also still repeated the same thing. We have Gao et al. 2010. They use EM and seismic method. People are not trusting just one method to solve the problem. That is the concept of and the philosophy of the joint multi-physics. You need to combine several of the physics to be able to have a more reasonable and confident interpretation. We have Gao et al. 2012. They did EM and the seismic. A lot of them are using EM and seismic. The same is for Hugh 2000 Hugh et al. 2009. And this set of people, Mokamp and the Mokamp et al., use more than two methods. They use EM, they use gravity, and also seismic method. That is once you understand the concepts, you will understand the need to combine several of them. Now, in the mathematical example that I showed you the other time, y equals to x squared, y equals to 4. What is x? X can be 2 or 4 or minus 2, sorry. But if you supply extra information like another physics, like the answer must be positive, then you are going to get a unique result and you stick with positive 2. But if there is no extra information, you cannot decide whether it's 2 or minus 2. You are going to stay confused. That is the need for the multi-physics. So the extra information that you supply is the multi-physics that helps you make a unique decision. We have Rachel and Rachel et al. And Bosov and Job. They did electromagnetic and resistivity joint inversion. Some people used electromagnetic and electromagnetic methods, and this Son and Lee 2012, and we have a Sonwall et al. 2013. You can see that a lot of people have accepted the philosophy of the joint inversion, and you should also try that because there are still many more researches to be done. And we want, a lot of problems are still not solved in the joint inversion. And if you are able to help us to solve those ones, that would be very lovely. And so we have, people are trying, but I think there are still more things to be done within that field. We have John and Morgan, 1996, and they used seismic and electrical tomography. Now, there are several aspects of joint inversion, the multi-physics. We need to think about constraints. How do you constrain your inversion? The constraint tells us what must be observed in order to get the expected results. The example, the mathematical example, y equals to x raised to power 2. If x is time, minutes, seconds, everybody knows that the answer must be positive because there is no negative time. So that's the constraint. You tell us that, oh, you're dealing with time. If you're dealing with distance, we can still have minus distance with respect to some reference point. So that's the role of constraints in multi-physics. You have to understand the problem, and then you must understand the constraints to impose. Several constraints have been imposed as well. And we have here, further C means coupling. And we have some people that impose petrophysical constraints. Gallardo is a popular author that popularized the use of cross gradients as the structural constraints to direct the joint inversion of DC resistivity and seismic data. Petrophysical constraint as well, Gao et al. 2012, they use petrophysical inversion, petrophysical constraints. You have some petrophysical relationship between electromagnetic data or resistivity and the velocity. You can also impose that. But at the start of the joint inversion application in geophysics, they did not impose any constraints. These people just combined the two data sets, and then they found a new result, and that was when the whole concept started. But nowadays, people try to include some extra constraints so that they can have better results. I also have published some papers along this line. I've published the joint inversion of seismic travel time and frequency domain urban electromagnetic data for hydrocarbon exploration. If you're familiar with frequency domain urban EM data, you will see that that is for the shallow near surface investigation, but the seismic method deals with deep imaging, where we have the hydrocarbon, we have the oil and gas located. Now, this concept is to supply information through the near surface, which is the frequency domain urban EM data, and to the deep surface through the seismic method. So we improved the velocity model for performing the stacking, the migration for the seismic method, and that also will help us to solve and image the hydrocarbon reservoir more reliably. The near surface has a lot of problems when we use seismic method, and if we can have some better image or more accurate resistivity image through the frequency domain urban EM data method, we can use that to improve on the image of the deep subsurface. That's the concept. The guy that I worked with on that same project built a velocity model through the joint seismic airborne EM inversion. So that's, people are applying it to solve several problems they think the joint inversion is capable of. Or in 2019, I published this paper as well, but I used EM and with agreement constraints. You know, if I come to Indonesia and I ask two Indonesians the same question about their culture, you know, if they give me different answers, I will not accept any of their answers. Why? Because I expect both of them to say the same thing. That's the concept here. I want to use EM and EM. I want the two of them to say the same thing. So if they say the same thing, I will be able to accept the results. And there's more confidence in the two results if both of them are the same. So I use this concept to provide more reliable resistivity image. I also apply the concept to publish this one, dotting the I and crossing the T of MIT resistivity models. I observed that so many of the published work also focusing on EM and seismic methods. So I thought about, okay, why not use gravity and magnetic methods, because those ones also need some joint inversion help. And the way that I applied it is also different from the way that have been commonly applied. And this one, I use it to map the geometry of the dense and susceptible body. And this one I use gravity. Gravity is similar to the EM that I showed you the other time. So you can see that there is still room for research and a lot of options are available that will help you to come up with your own research topic. And you must be producing unique results. You cannot just rely on one method these days. So I will present the result that I published in um, in 2019, where I used the EM, and the journal name is Earth and Space Science. This is another way of performing the joint inversion. Like I told you, if I ask 10 Indonesians about a question concerning their culture, and if the 10 of them say the same thing, you know that I don't need to Google anymore. I just accept the answer because they are saying the same thing, and that is more reliable. But if I ask them and they are giving me different answers, then I can just ignore the answers. So that's the concept I used here. And the approach make use of a single parameter of the buried geological target, which is the conductivity in this case, because the EM method help us to target the conductivity or resistivity of the buried different data set we choose to use at the time and the frequency domain airborne EM data. Now, the complementariness and constraints. Equally important are those things that we must factor in. The methods must complement each other. We must avoid redundancy in contribution. For instance, the mathematical example I gave you, y equals to x raised to power 2. If you need to supply extra information that will be complementary, you cannot give me the same equation. That's not useful. You have to give me something that will help me to get the unique answer. Combined data methods must synergize the strength to improve the overall final output. And the constraints, like the cross gradient, is the structural constraint. We have petrophysical and reservoir constraints. We have functional constraints, Riemann constraints. The cross gradient is also popular. They are available in the absence of petrophysical or other constraints. If you don't have petrophysical information, and the cross gradient is useful. But there are so many limitations in the cross gradient constraints. The cross gradient constraint does not work when the geometry is less than 2D, two-dimensional, because model parameters from the other dimensions must be used to compute the cross gradient. And that will necessitate the use of pseudo 2D grid. The gradient constraint is similar to the cross gradient, but this one uses dot product. Dot product is 1 by 1, whereas the cross gradient is across dimensions. So the cross gradient, the gradient constraint does not have the limitations of the cross gradient. It also exploits the underlying physical relationship between the interacting medium parameters. Therefore, our objective is to perform the gradient constraint joint inversion of the time and frequency domain airborne EM data. Now, this is the method. If we take M1 and M2 as the logarithm of the resistivity of time and frequency domain EM data, respectively, the gradient matrix is formed from the dots product of M1 and M2. The objective function to minimize for the gradient constraint is given by equation 1, where the GI and the DI are respectively the computed and the true height data. We have SMN and SG as the regularization term, and also the Gramian stabilizing function that enforces correlation between M1 and M2. The scaling factors for SMN and SG are alpha and beta respectively. This, if you check Jordanov 2015, you will see how this equation is minimized. And once it's minimized, it can be solved by iterative regularized conjugate gradient method. Now I'll give some examples, starting with a synthetic example. And also after that, I'll give the true model example. The synthetic example is seen in figure. The true model resistivity model is in figure 1. The background resistivity value is 100 ohm meter. On the left, the block there is 500 ohm meter, while the block on the right is 30 ohm meter. They are buried in the subsurface. The time domain, airborne EM, and the frequency domain, airborne EM are used. Methods are used to acquire data. And we have 7 data points. The number of layers used there is 6, and each layer is 5 meters thick. The resolve system is used to acquire the frequency domain data, while the SkyTerm is used to acquire the time domain data. The resolve is flown at 20 meters with horizontal receiver offset of 7.93, and it acquires horizontal coplanar in-phase and quadrature responses at 5 frequencies. And the SkyTM is flown at an altitude of 40.55 meter, station spacing of 13.26 meter, and the off time is 4.167 milliseconds. We perform 10 standalone iterations. That is not joint inversion. That's what is called a standalone. And we performed that before commencing the joint inversion. I added several magnitude of noise to the data from 0 to 3% random noise to check the robustness of the results. And this is, I present the result for you now. After the 10 standalone iterations, we have this figure in figure 2, the ones on the top. We have the standalone time domain. From the time domain, this is the result on the top left. The frequency domain we have on the right, top right. You can see that if you have these two, let's say the one on the top left hand side, top left is an Indonesian, and then this is another Indonesian, and they're giving me 2 different responses to the same question. I get confused. We don't know which answer to go for. That's the confusion in non-uniqueness. It's not unique because the answers are completely different from each other. This one has some smearing to the surface here, while this one has clean job, and all of that, they are different. But look at the joint inversion in the top, at the bottom left, from the time domain, which is for the noiseless, and the bottom right for the joint frequency domain noiseless. Now, these results are coming close, and these results are more reliable because they are talking and speaking the same thing, almost the same thing. And this one is more reliable than this. This is confusing. And that's why the joint inversion is helping us to move towards unique interpretation. So we checked for the, okay, what if we increase the noise in the data? I checked that as well, 1% and 1% here. You see that both of them are still saying the same thing, that the structures are close to the true solution. You can rely on this. And then you have a joint inversion for the 3% noise. They are saying the same thing. Actually, this must be higher than 3%, but the result is still very robust. You can rely on this. That is the That's the benefit of the joint inversion. They help you to have consistent and reliable results. Now, figure 4 shows the correlation coefficients, the convergence cross plots with iterations. And we observe that now this is the first, the black one shows the standalone iteration. You know, I performed 10 iterations before starting the joint inversion here. So you see that the correlation coefficient is very small here. But as soon as we introduce the joint inversion through the cross gradient, the correlation jumps up, although it reduces with noise content. And the data misfit is also quite small. We have the cross plots telling you that the result must be the same because we are looking for the same object anyway. So that is the result from that. From all this analysis, you can confidently accept the result there. And the data feed for the synthetic airborne EM data overlay is presented in figure 5. You can see that the data fits well, the computer data fits well with the true data set at all frequencies for the frequency data and at all data points for the time domain airborne EM data. So the next thing to do is, okay, what about field data? Because you cannot just be testing on synthetic data and then you don't have a way of checking your results on the field data. So I use the data from the Bukpalong irrigation the system was flown at altitude of 33.46 meter with horizontal receiver offset of 7.86 meter. And it was acquired for coplanar in-phase and quadrature responses at high frequency, just like the case of the synthetic experiments. I use the moments sky time data for the time domain, and the system was flown at 39.8 meter altitude, horizontal receiver offset of 12.4 meter. The off time is 4.167 meters milliseconds, and the two data sets were acquired at different times. The time domain was acquired in 2016, and the frequency domain data was acquired in 2008. That's 2 years time lapse there. The resistivity model has 10 data points, and the number of layers that I used was 14. I performed 6 standalone iterations before 10 joint inversion iterations. Now, this is the results that I got from that. Though in figure 6, then figure 6A, we have the standalone without the joint inversion. You see, like I said, the red one is a frequency domain result, and the blue one is the time domain. Both of them are saying different things, just like if two Indonesians are saying the same different things for the same question, it's not reliable. You don't know which is telling the truth. So this one is not right. So, but if you look at the joint inversion in figure 6B, you see that both of them are saying almost the same thing. The difference between them is attributed to the 2 years of interval, 2 years interval that was between the two data. And they were acquired at 2 different times. 2 years. 2 years is a long time to change the properties of resistivity model, because that area was prone to salinization. Salt water was flowing from irrigated water. So that would change the resistivity model quickly. But you can see the effect of the joint inversion, that they still say the same thing. closely match. You rely on this result more than you do of these standalone. This is non-unique. We don't know. One is telling you -2 and the other one is telling you +2. You're confused. You don't really know. But when you have this, you can rely on the results here. And that's the beauty of joint inversion. And the results, like I showed the other time, the data misfit and the cross plot are saying the same thing. We have data that is feeding well, and we have the scatter plot, the cross plot also agreeing, telling us that we are doing a good job. So in conclusion, I have discussed the multi-physics from the frequency and time domain airborne, EM, data that have been jointly inverted with Riemann constraint, which is the dot product of two resistivity model vectors. The Riemann constraint synergize the linear correlation between the resistivity models to produce more reliable images than those from the standalone. The application of the concept on synthetic data proves the compelling role of the Riemann inference in the joint inversion, even in the presence of noise. Increasing linear correlation coefficient and decreasing data misfit with iteration is further ensured by the Riemann constraint. Moreover, the frequency and the time domain airborne electromagnetic data from the Bukpanang Irrigation District, South Australia, have been jointly inverted with Riemann constraints, which reveals a resistivity background of 1 ohm meter with a stabilized lower resistivity values and the near surface, the shallow depth. So these are the references, some of the references cited in the presentation. I want to thank you for listening. And if you have any question, I think I will send you my email address now so that you can, I can still answer some questions before leaving. And I want to thank and appreciate the support of the Brain Korean 21-4 program. And I want to also thank you for listening. So I should answer some questions now. Thank you.
Okay, thank you, Prof. Ogunbo, for the presentation. Very interesting, but we have limited by time. So do you still have a time to question and answer, or?
Yes.
Okay, so to every participant, if you have any question, you can raise your hand or you can write in the chat box. Thank you. And before we end the session, we have the photo session, so please stay in this room. There is a question from Miss Rizka. Can you see in the chat box?
Yeah.
Okay, you can answer directly. Thank you.
Okay. In joint inversion modeling, we use more than one physical parameter. You know, when we inversion priority. To really do. How to relate those different physical properties in joint inversion? Okay, there are several constraints to understand. If you want to solve your problem, I think the first thing is to understand your goal. on the targets, because like the mathematical example that I gave you, there is nothing wrong with this equation y equals to x squared. But if I want a positive answer, I know that I'll go for x equals to 2. And if I need negative answer, I'll go for x equals to -2. So that is the understanding there. You have to be able to understand the basic things that you are doing. And then if you want to combine gravity and density, for instance, together, gravity and seismic methods together, you know that you have the Gardner's equation that can help you. And that one is going to guide you. Let me see the second question. What method do you usually use to determine the uncertainty of the joint inversion with field conditions? It is the same method that you use for determining the single in physics. It's not different. This one is just combining two. That means you're going to use the same for each of the methods that you have there. Let me see. I want to ask about the joint inversion of seismic velocity and EM data. Can you explain more about it, or where can I get a reference? Okay. I can send you the reference. I think I showed so many references there. You can replay this. You have several references of EM and the seismic method. There are quite a few of them, so many of them. And if you go to the list of references at the back as well, you have some there too. So I think that's what I can do for now. And if you have further questions, just send to my email address. Yeah, I use this one most of the time. That will,
okay.
Yeah.
Yes. Thank you very much for the answer, and thank you for the question, Ms. Rizka and Mr. Muhammad Risa Pardana. So this is the email address for Prof. Ogunbo. You can send your question here. So the next is the photo session, but before that, Bapak Dr. Wahyudi, do you have something to say? Please.
Yes. Thank you very much for Professor Ogumbo. So on behalf of our Department of Geophysical Engineering, we thank you very much for your attendance and for your lecture, this international virtual course. Yeah, this is useful for us, for our students, and also for faculty member. Yeah, so we hope to meet you again, to see you again next time in another event. Yeah. Okay, thank you very much.
Thank you. Bye-bye, everybody.
Thank you. So, everyone, please turn on your camera. We have the photo session. Okay, thank you. So, Prof. Ogunbo, please join with us. The first slide, 1, 2, 3. The next slide, 1, 2, 3. Okay, wait. The next slides, 1, 2, 3. The last one. Wait. Okay, thank you everyone. See you again in the session 2 this evening. Thank you very much, Prof. Ogunbo, for your lecture for today.
Yes.
Okay, thank you very much.
So, to all participants, the session 2 will be following with the some quiz. you can download the materials in the chat box, and you can rewatch the meeting recording in the FTTM YouTube channel. Thank you.
Okay, Harmita, we don't have a slide from Professor Ogumbo, but the three files you sent is the material from Professor Budi Sulistyo. 4, yeah, 4, 1, 2, 3, 4, yeah, 4 or 5 files.
Where is the file, Pak Wahyudi? I can see the file.
Sorry, Harmita, you can close the session.
I still send some files, Pak.
I don't have the file. Professor Ogumbo's file. I don't have it.
Oh, okay. This is the file from previous session.
Previous session, yeah, from
yes.
Professor Budi Sulistyo's slide.
Also from Pak Arif Munandar. I resend the file.
Okay.
Okay, everyone, I end this session. Thank you.